Hi everybody, it's Mr. Oliver. I'm going to go over the solution for free response question number 2 for the AP Physics 1 Unit 6 review. Let's go and get started. Okay, so for this question, and I know it's kind of blurry there, guys. It says a block P of mass M is on this horizontal frictionless surface, so that's this guy. And it's going back and forth on this little spring mass system oscillating. It tells us it's got a period of T subscript P, and an amplitude of A sub P. And the equilibrium position is right here in the middle, it's marked. Then we're going to drop a second block labeled Q that's twice as heavy on top of it as it passes through here. So this thing's going back and forth, and as it's passing from right to left, we drop this block on top of it, and it immediately sticks to the top. And then the two block system oscillates with this new period and amplitude. And first of all, it says we want to determine the numerical value of the ratio of TPQ to TP. All right, so that's the easiest part. So TPQ is equal to 2 pi times the square root of the mass of that system divided by the spring constant K. Well, in this case, whenever the two are stuck together, the total mass of that system is 3m. So we've got to make sure we include the fact that that mass is 3 times the regular mass. So it's going to be 2 pi times the square root of 3m divided by k. Now, the original period is just 2 pi times the square root of the mass of that system divided by k. It's still the same spring, and so that's 2 pi divided by the square root, or times the square root of m over k. Now in this question it says want us to determine the ratio of these two terms. So essentially all I'm going to do is divide those two terms together, or in other words divide these two terms together because they're both equal. And so you'll see that the 2 pi goes away, the square root symbol, because you got square roots on tops and bottoms, those cancel out. The m's cancel out because they're in the same place on the top and on the bottom, and also the spring constants cancel out. And so really, it's not that the square roots go away, it's just all the terms that are inside the square roots can cancel. And so that leaves us with the square root of 3 over the square root of 1, essentially, which is just the square root of 3. Sorry, I shouldn't have said that the square roots cancel. They don't really cancel. It's just that the terms inside of them can cancel. All right, so that's for part A. Now part B says the figure is reproduced above. How does the amplitude of oscillation of APQ of the two block system compare with the original amplitude? All right, this is a tricky question because what we need to do is we need to understand what's happening when these two things come together. Well, when they come together, they stick together, right? And so if they stick together, initially you've got one block P, traveling to the left at some kind of a velocity. And then afterwards, you've got this two block system coming along with some kind of new velocity. Call that a final velocity and call this an initial velocity. Well, here this P and Q system has a total mass of 3m, right? Here you've only got a mass of m. So effectively what's happened here, when you drop this block on top of it, it's almost treated as an inelastic collision. Because when you have one object with a certain amount of momentum, and then you got a combined object with a certain amount of momentum, assuming there's no outside forces, which there's not, because nothing pushed the block one way or the other, it's just dropped straight down on top of it, then that means that this momentum is conserved. And so we can say P initial equals P final. Now, I don't know exactly what the speed is. I can calculate it if I wanted to. But if I look here, P initial is M1 V1 initial. That's going to be all this momentum. P final is going to be 3M times V final. And so this mass term is going to cancel. And so that means that our initial velocity is 3 times the final velocity. Or in other words, the final velocity is 1/3 of the initial velocity. And so since it's moving slower, you can conclude that the time it takes to complete one oscillation is also going to be slower. So what has to be true is that the period does change. It definitely does change. But really what you need to say is like, well, what happens with the amplitude? Well, if this is a inelastic collision, the other key point is that inelastic collisions do not conserve energy. Do not conserve energy. Well, how is that relevant? Well, if you think about the oscillation, the energy of an oscillation, the total energy, is 1/2 times k times a squared. And that's the total energy of that system. So left to its device, it's got some kind of oscillation back and forth with some kind of an amplitude back and forth. Well, once you add this big mass to it, that amplitude has to go down because it's an inelastic collision. It doesn't conserve energy. So what's going to happen here is that as that energy decreases, in order to maintain that equality, the amplitude has to decrease as well. So what you can conclude is that the amplitude of this PQ block combination must be less than the amplitude of the P block system by itself. All right. Something else you want to mention here is that since the collision occurs at equilibrium, that's a point of maximum kinetic energy. And because we're going to take away from that maximum kinetic energy because it's an inelastic collision, what has to happen is the potential energy is going to be less as well. All right, so when think about it, when you add this block, the speed goes down. It's 1/3 of the original speed. And because the speed is less, the kinetic energy is going to be less. And because energy is conserved, it has to stand true that the potential energy will be less. And potential energy depends on how far it moves, one way or the other. All right. And if you wanted to go through any set of calculations, you can. Let's just make up some numbers. So let's say that let's let our spring constant be 50 newtons per meter. Let's let mass of P be 10 kilograms. Mass of Q is twice as much. It was 2m, so we're going to call that 20 kilograms. And let's just say the original amplitude of P was 0.7 meters. Okay, so let's calculate the period of P first. That's 2 pi times the square root of m over k, which will be 2 pi times the square root of 10 over 50. And you get 2.81 seconds, sure enough. Okay. And then from that, I'm also going to take some time and calculate omega, because I'll probably need that later. Omega is 2 pi divided by the period, which is 2 pi divided by 2.81, and that's 2.236. Okay, so that's our angular frequency. I just like to have that on hand. Now, let's look at my Vmax, my maximum acceleration, or maximum velocity. So that's A times omega. So that's 0.7 times 2.236. So that's 1.565 meters per second. That's my maximum speed. And my max acceleration is going to be A omega squared, which is, plug my numbers in, I get 3.5 meters per second squared. Okay. Now, how is that going to help me on the rest of this? Well, if I go in and do these calculations now for conservation of energy or conservation of momentum, I could say that 1/2 mv max squared would be with this additional mass is going to be 1/2 times the total mass, which is now 30 kilograms. And then and if I also, I need to calculate the final speed. So P initial equals P final, go through this process, and we find out that the final velocity is 1/3 of the original velocity. Remember that? So if my original velocity is 5.625, and now it's 1/3 of that, it's going to be 0.518 meters per second. So that's my new final velocity, my new maximum. And so when I plug that number in here, 0.518 squared, I'll set that term equal to my amplitude, 1/2 Ka squared, of this new system with this added mass. So that's going to be 1/2 times 50 times this new amplitude. And that's what I'm looking for. I was looking to find out what this new amplitude is. And so when I do the math here and I solve for my new amplitude, APQ, I end up getting 0.401 meters. Whereas before, it was 0.7 meters. And so this is just a numerical proof, just making up numbers, assuming everything's equal, that sure enough, my original amplitude has to be bigger than my final amplitude. Now, you're not going to be expected to do this on an AP exam, but I just wanted to show you that the reasoning and the fact that it's an inelastic collision makes that amplitude goes down should hold true when you do the mathematics. All right, guys. If you do have any other questions on that one, please let me know. That concludes the solution for this. But guys, I hope you have a great day, and I'll talk to you later. Bye-bye.